This is where the rabbit come out of the hat. Okay? This is like, you don't even know there is a rabbit. You don't even know there is a hat right now. You're totally wasted. Like, what is she going? Like, pulling the rabbit out of the hat. What hat? What is she talking about? The leek, the pastrami, the cheese. What's going on? Right? Okay. The rabbit comes out of the hat is this part. See this defy dx? Here is the rabbit. Okay? This is the rabbit, and this is the hat. The rabbit can come out of the hat. It can come out of the hat, why? Because defy dx is constant over the cross-section. Defy dx does not change with r. It's the same on every point of the cross-section. So this rabbit, out of the hat, here. And that helps us immensely. It helps us immensely because look at this thing. If I take 2 pi times r times dr, what is 2 pi r dr? What is that? The 2 pi r dr, if I take this thing, what is the cross-sectional area of this ring? No, pi r square. This is just a thin shell of radius r. Yes, 2 pi r dr. You cannot take a hint. So I'm killing you guys, killing you. Okay, this thing is 2 pi r dr. So 2 pi r dr is the area. Defy dx came out of the integral. So if I put it all together, I get that my t of x is equal to defy dx times the integral of r squared times g of x and r times the area over the area. Right? Fantastic. Now, this guy here, you remember what we did in axial loading? We said the integral over the area of E times the A. This we call it the EA effective because we are integrating over area at x, right? This is what we call EA effective of x. Remember? In axial loading, all what matters is how stiff the area is and how big the area is. In axial loading, we don't care how far away we are from the axis. In torsion, we care how far we are from the axis. So my resistance, if I want a certain defy dx at that section, I need to give it a torque that scales not just with the area, not just with how stiff the material is, but with how far my area is from the center of the axis. That's why if I take something with a big radius, even if it's thin, it's very hard to twist it. Okay? All right, so the same way as this one was our EA effective, this thing, which is G, and it has R squared dA, looks familiar? R squared dA is the IP, the polar moment of inertia of the section. So this is G, IP, effective of x. So this whole thing becomes simply defy dx times G, IP, effective of x. So how do I calculate GIP effective? Well, if the shaft is homogeneous, then it's fairly simple, because when I integrate GIP effective, I can take it out, and I get G. So if it's homogeneous with modulus G, I get G times R squared dA. And so this is equal simply to GIP. Right? That's why it's called GIP effective. If it's homogeneous, I take the G out, and I get G times the IP of the cross-section. If it is not homogeneous, if it's a composite shaft, say that I have something like this, in which I have a material 1 that is modulus G1 and area A1, and I have a material 2 that has modulus G2 and area A2. Then what I do, I take this integral here and I split it up. It's going to be G1 times the integral over area 1 of R squared dA plus G2 times the integral over area 2 of R squared dA. And this is going to be G1 IP1 plus G2 IP2. Same as we were doing E1 A1 plus E2 A2 in axial loading. Okay, so for composite, you need to sum the contribution. Remember, when you sum the contribution, if you were doing axial loading, your area 2 here would be the thick ring, would be pi r square out minus pi r square in, right? That's the same thing with IP. If you have a composite shaft, then you do the IP of the outside using this, and you do the IP of the inside using that. Okay? We are done. We are done. We are absolutely, stunningly done with axial loading. So how do we solve problems in axial loading? Let me give you the path. So, yes, living in the past. That's what I do all the time. Not axial loading, but torsion. What is the path to solving problems in torsion? It's a path that should be very, very familiar to you by now. It's the same path we were doing in axial loading. From the loading, you get T of x. And this is the last thing we got to do in the last 15 minutes. From loading, we get T of x. From geometry and material properties, by material property, I mean G, we get G IP effective of x. Notice that GIP is not a function of R. Do you see? GIP is only a function of x. GIP is integrated over the cross-section. That's the contribution of all the area. Right? GIP is a function of x. Torque is only a function of x. Out of these two, I invert that relationship over there, and I get that my d phi dx is equal to T of x divided by my G IP effective of x. This is the same as when we said du dx is equal to n of x divided by EA effective of x. This was the center of solving all my problems in axial loading. This is the center of solving all the problems with torsion. Get your torque resultant, get your GIP effective, you get d phi dx. What do you do with d phi dx? d phi dx is the center of the universe. d phi dx, you can do two things. You can get your strain at any point in the shaft, at any r and at any x, simply doing r times d phi dx. And from the strain, you can get the stress in any point, in any radius r, as a function of g at that point. So say the tau in material I is going to be g of material I times r d phi dx. This is the same as when you were doing the stress equal Young's modulus of the material times du dx. So out of d phi dx, one path gives you the strains and the stresses. What is the other thing that you do with d phi dx? You integrate in x. integrate in x. So when you integrate in x, if you simply integrate starting from where you know something, phi 0, phi of x0. Phi of x0 is the phi at the wall, 0 at the wall. So what is the rotation angle at any position x? What is phi of x? It's going to be phi of 0 plus the integral of d phi dx from 0 to x. The same way as u of x was the integral of the u dx. So phi of x is phi of x0 plus the integral from where you know things to where you wanted of d phi dx in dx. Okay? Same as we were doing in axial loading, but now instead of u, there is phi. Okay? So phi of x from where you know it to where you want it. And of course, the total angle of twist is going to be the integral from 0 to L of d phi dx. And notice that this one is the same as saying phi of L minus phi of x. That's it. This is how you solve problems in torsion. This is the whole story on this board. Okay? Why is that phi of L minus, oops, sorry, here. Sorry, absolutely. That was not the whole, that was the whole wrong story for torsion. Okay, thanks. Okay, yes?
So the first line you have phi is equal to r, oh, I'm sorry, what is that? I can't get these symbols correct.
Where? Too much Greek here.
The first line.
The first line up here?
No, the first line of what, yeah, right there.
Gamma is the shear strain.
Right.
Like if you go to that board, is shear strain, gamma.
Okay, so d phi dx times r is gamma, and then as well as the tau is, okay.
The tau, we did it here, right? We said the tau is how much strain I have, which is this, times the modulus.
So that's each mod.
Each material. So if I have steel, that would be G of the steel times that, if I want the tau in the steel. If I had aluminum, that would be tau of the aluminum, would be G of the aluminum. Okay, like the same way as here we said, no, we don't have that anymore. Yes?
What is the Greek letter for angle of twist called?
Oh, that's a capital phi.
Okay, is that the lowercase phi?
Yes, so this guy here is capital phi, and this one is lowercase phi. Didn't you take Greek, for goodness sake? I'm sorry. Yeah, I should have been a little clearer in what the names are with all these letters. Gamma, tau, gamma. Okay, so this is gamma. This is tau. This is phi. This is capital phi. And what else we have? Then we have the curly T and epsilon. Epsilon, sigma. Anything else? Delta. And theta, the angles. Anything else we have in Greek? Okay. You think you're coming to do engineering, but really this is an education in the classics. Okay?